Each trial of the simulation requires a value for the direct labor cost. Suppose that on the first trial, the random number is 0.9109 from table point 11. From table 11.1, because 0.9109 is in the interval, so the corresponding simulated value for the direct labor cost is 47 per unit. And if the random number is 0.2841, the simulated value for the direct labor cost is $44 per unit. So each trial in the simulation also requires a value of the parts cost and first year demand. Let us now turn to the issue of generating values for the parts cost. The probability distribution of the parts cost per unit is the uniform distribution that is shown in 11.3. So because this random variable has a different probability distribution than direct labor cost, we use random numbers in a slightly different way to generate simulated values for parts cost. So to generate random numbers or a random variable, a value characterized by a continuous uniform distribution. So using the Excel formula. So value of uniform random variable is equal to the lower bound plus the difference of the upper bound and the lower bound multiplied by the random numbers. So for Sonatronics, the parts cost unit is uniformly distributed random variable with a lower bound of $80 and an upper bound of 100. So applying the equation, we have the parts cost is equal to 80 plus 20 multiplied by random numbers. So 80, which is the lower bound, plus the difference between lower bound and upper bound is 20 multiplied by the random numbers. By closely examining equation, we can understand how it uses random numbers to generate uniformly distributed values for parts cost. So the first term of the equation is 80. Because Sonatronics is assuming that the parts cost will never drop below 80 per unit. So this is the lower bound. Because rand is between 0 and 1, the second term, 20 times rand corresponds to how much more than the lower bound, the simulated value of parts cost. So because rand is equally likely to be any value between 0 and 1, the simulated value for the parts cost is equally likely to be between the lower bound 80 plus 0 is equals to 80 and the upper bound 80 plus 20 is equal to 100. So for example, suppose that a random number of 0.4576 is generated by the random value or random function. As illustrated in the figure, parts cost is equal to 80 plus 20 times 0.4576 is equal to 80 plus 915, that is equal to 89.15 per unit. Suppose that a random number of 5842 is generated on the next trial, the value for the parts cost would be 80 plus 20 times 0.5842 is equal to 91.68 per unit. With appropriate choices for the lower and upper bounds, the equation can be used to generate values for any continuous uniform probability distribution. So we need a procedure for generating the first year demand for computer-generated random numbers, because the first year demand is normally distributed with mean of 15,000 units and a standard deviation of 4,500 units. We need a procedure for generating random values from this normal probability distribution. So again, we will use the random numbers between 0 and 1 to simulate values for first year demand. So we get the demand is equal to norm dot end. That is with the parameters of random numbers and the distributed mean and the standard deviation. So which implies 60.26% of the area under the normal curve is to the left of this value. Applying the equation, so we get the formula is equal to norm dot end, that is the inverse of the normal cumulative distribution for the specified mean and standard deviation. Which implies that 60.26% of the area under the normal curve is to the left of this side. Okay, 60.26, which is on the left of this side for the generation of the value for first year demand, corresponding to the number of 0.6026. And the static values in figure 11.1 for these parameters in cells B6, B7, and B8 are replaced with cell formulas B6, B7, and B8 that will randomly generate values whenever the spreadsheet is recalculated. So in cell B6, it uses the random number generated by the rand function and looks up the corresponding cost per unit by applying the VLOOKUP function to the table of the intervals contained in cells A15 to C19. C19, A15 to C19. So from the lower end of interval up to the cost per unit. In B7, it executes the equation using the cell references to the lower bound and upper bound of the uniform distribution of the parts cost in cells B22 and B23 respectively. B22 and B23, the lower and upper bound. And also, the B8 executes the equation of 11.6 using the references to the mean and standard deviation of the normal distribution for the first year demand in cells D22 and D23. D22 and D23. So in simulating or in executing simulation trials with Excel, so each trial in the simulation involves randomly generating values for the random variables. Random variables like labor cost, parts cost, and first year demand, and the computing profit. To facilitate the execution of multiple simulation trials, we use the Excel's data table functionality in an unorthodox but effective manner. So to set up the spreadsheet for the execution of 1,000 simulation trials, we structure a table as shown in cells A25 through E1025. So there are the rows 47 through 1024 are hidden. Cells B26 to E26 contain references to the cell or cells corresponding to direct labor cost, parts cost per unit, demand, and profit. So to populate a table of simulation trials in cells A26 through E1025, we execute the following steps. So first, select cell range A26 to E1025. Click the data table or data tab in the ribbon and click what if analysis. So that is, we have applied what the steps or same steps using the data table that you have learned in the previous chapter in building the spreadsheet models. So we have to follow the steps until the end.